our last section for our Math 272. So the last thing I have to teach you this semester is conic sections and polar coordinates. There's no new calculus to learn. The calculus that we'll do is to compute the derivative and locate horizontal and vertical tangents, and that's just the same as what we did back in the past section with any polar graph. So we just need to look at a polar form of a conic section, compute the eccentricity, and the eccentricity tells us the type of conic that it is, and then we can use that to sketch the conic. So it's a unified treatment of all three types of conics. Remember, the three types of conics are ellipses, hyperbolas, and parabolas. It's just two cones, and you cut it with a plane. If you cut it one way, you get an ellipse. If you cut it flat across, it would be a circle, which is just a special case of an ellipse. If you cut it completely vertically, you would have a hyperbola, and at an angle, you have a parabola. If you cut it at exactly the right angle, correct angle, you get a parabola. But the eccentricity is a way of measuring these and identifying them. If you have the focus and a fixed line called the directrix, E is a fixed positive number, and the set of all points in the plane such that the distance between a point and the focus and a point and the directrix is equal to E. So that ratio stays the same. If E is less than 1, you have an ellipse. If E is equal to 1, you have a parabola. If E is greater than 1, you have a hyperbola. Here's the pretty picture showing a parabola. Sorry, I got distracted by the fact that it changed my picture right there. I'm going to go in and fix that. So this shows the different forms of the parabola. If you have ED over 1 plus the eccentricity times cosine, then the directrix is to the right of the parabola and it opens to the left. If you have cosine and a minus sign, then it opens to the right. If you have sine with a plus sign, the directrix is above, and if you have sine with a minus sign, the directrix is below. Honestly, I do not memorize all of that. I plot the big four, and that tells me exactly how to graph. So, a polar equation of this form, ED over 1 plus or minus E cosine or sine theta, is a conic section, and the eccentricity is the number sitting next to the trig function. So we have R is equal to ED over 1 plus or minus E cosine theta, or ED over 1 plus or minus, not plus or minus, just plus or minus E times the sine of theta. Ellipse, E is less than 1. Hyperbola, E is greater than 1. Parabola, E is exactly equal to 1. And when we start to graph these things, you're going to see why it works that way. So let's look at this one. Step number 1, when you're given a conic as a polar equation, get it into the form where you have a 1 sitting right there. Then your E will be sitting next to your trig function. So for example, 1, we have R is equal to, I'm going to go ahead and divide everything by 3. So I have 10 over 3 sitting on top. 3 over 3 is the one that I wanted, minus 2 over 3 cosine theta. Now, since it's cosine, I know that my directrix is going to be an x equals function. And since it has a minus sign there, I know it's going to be x equals minus d. But even if you don't remember that, go ahead and figure out what your d is. We know eccentricity is equal to 2/3 because it's the absolute value of this number sitting right here. 2/3 is less than 1. That means we have an ellipse. So ED is equal to this number sitting on top. And E is equal to 2/3, so 2/3 times D is equal to 10/3, so D is equal to 5. Now I know that X is equal to -5 is going to be my directrix. You have one focus sitting at the pole. So I'm going to make my little chart, just like I always do. And I usually go back to the original function, so theta, and I go back to 10 over 3 minus 2 cosine theta when I'm plugging stuff in, just because it's a little easier for me to plug things in there. 0, pi halves, don't know why that popped up, pi, 3 pi halves. So when I plug 0 in, I get 10 over 3 minus 2, so 10 over 1. When I plug pi halves in, I get 10 over 3 minus 0, 10/3. At pi, I get 10 over 3 minus -2, so 3 plus 2. And when I plug 3 pi halves in, I get 10 over 3 minus 0, 10/3. When your eccentricity is less than 1, you'll have 4 positive numbers when you plug stuff in. So I'm going to go ahead and sketch a tiny little graph right here. So my big number is here at 10, so 2, 4, 6, 8, 10. And then 2, 4, 2, 4, 2. At pi, it's 2. 10/3, so this would be a little more than 3, so 2, about right here, and about right here. So we look something like this, except, you know, more like a ellipse and less like a guitar pick. But that's okay, I do the best that I can. And then my directrix would be at -5, so this is 2, 4, 5 would be about right here. So that's how you can figure out the location of your other focus. And then there would be another directrix on the other side. So let's talk about the other focus. I find the distance from, actually the focus is right here, so the distance from the focus to the directrix, or you could find the distance from here. But just to find the other focus, we don't need the directrix, we need the vertex. The distance from the vertex to the focus is 2 units, so I have another focus right here at the point r theta, so 1, 2, 3, 3, 0. And then the other directrix would be over here, and since it is 5 units away from this focus, it would be 5 units away from that focus. So at 3, and I think I don't have this plotted right because this was 2, 4, 6, and that's okay. Let's look at the pretty picture before I get any more confusing. So the polar coordinates are 0, and here's one focus. It's 2 units away, so you would have one 2 units away from 10 here. So that would be not at 3. It would be 2 units away. It would be at 8. It would be right here. Because this is 2, 4, 6, 8. This was at 2. So 2 units from this vertex to this focus, 2 units from this vertex to this focus. Then I had this one at 2 and 5, so this one would be 10 and 13. Okay, so that's how you find, you just make them even on either side. Alrighty. Let's do another one. Okay, I wrote it down. I divided everything by 2 so that I could have a 1 right there. That means my eccentricity, E, is equal to 2, which means greater than 1. I have a hyperbola. E times D is equal to 6. So 2 times D is equal to 6. D is equal to 3. I have a plus sign here and a sign, so my directrix is y equals 3. Now let's make our little chart with the big 4. We have theta and we have, I'm going to go ahead and put in 6, 1 plus 2 sine theta. Easy to plug in. So I have 0, pi halves, pi, 3 pi halves. I plug 0 in. I get 6 over 1 plus 0. I have 6 over 1 plus 2. So 6 over 3 is 2. I have 6 over 1 plus 0 is 6, and I have 6 over 1 minus 2, so I have minus 6. So, minus 6 is special. It is the one that is the other side of the hyperbola. Now, hyperbolas have 2 little arms. So here's one arm, and negative 6 is the co-vertex of the other arm. Let's graph it. So I'm going to graph the 3 positive numbers. 0 and 6. 1, 2, 3, 4, 5, 6. I won't count by 2s. 2, 3, 4, 5, 6. And 1, 2. So these I can just play connect the dots. Then I plot my other point, which is 1, 2, 3, 4, 5, 6. It's right here. I like to go ahead and draw in my directrix at y equals 3. So this was 1, 2. Y equals 3. There's another directrix that is 1 unit away from this co-vertex. So y equals 5. Then I count how many units I am. So this is 2 units above. So I'm going to be 2 units above this line. So here, here, and I'm going to draw a dashed line there. Then I have to just reflect this about there. So since this is 2 units away from the vertex, and this is at 6, I'll put this right up here. And I do the same. I follow this one right up here. And I have reflected it, and I have my perfect hyperbola that I need. Here's the pretty solution. There I put in the directrix. Then I plotted that point, and then I found the correct distances. So the effect of E on the conic. If your E is closer to 1, then your ellipse is closer to a circle. If your E is closer to 0, then your ellipse would be longer and skinnier. I had that backwards. If your E is closer to 0, then you're closer to a circle. The bigger your E, the flatter your ellipse gets. The bigger your E is, the flatter your hyperbola is, and the same with a, well, with a parabola, your eccentricity is just 1. We did not draw a parabola, so let's do the practice problem together that's going to give us a parabola. Now, if I look at the first one here, I have r is equal to 4 over 5 minus 4. I'll divide everybody by 5. Not a parabola because the eccentricity is not equal to 1. This one is going to give me an eccentricity equal to 1. So let's go through this one together, and then I'll leave the others for you to do on your own. So, practice parabola. We have that r is equal to 2 over 3 plus 3 sine theta, which is 2/3 over 1 plus sine theta. Eccentricity is 1, which implies a parabola. E times d is equal to 2/3, but my eccentricity is just equal to 1, so d is equal to 2/3. I have sine, and it's positive, so y equals 2/3 is my directrix. Parabolas only get one directrix and one focus, so it has a focus at the pole, and that's its only focus. Now let's make our little chart. We have theta, and I'm going to go back to this one to minimize the number of fractions. 0 pi halves, pi, 3 pi halves. So I have 2 over 3 plus 0. I have 2 over 3 plus 3. I have 2 over 3 plus 0, and I have 2 over 3 minus 3 undefined. With parabolas, you'll always have one that's undefined. That's the side it opens up to. So this one opens down. Let's plot stuff. And first I'll plot the directrix at 2/3. So we'll say this is 1/3. This is y equals 2/3. So this is 1/3. Let's see. Well, that happens to be where we plot at pi halves. 1/3, 2/3. 1/3, 2/3. I focus here at the pole, and it lives right in the middle between the vertex, lives right in the middle between the focus and the directrix, because it always has to be the exact same distance between the two. Okay, so what else were we supposed to do? We have found the eccentricity, we identified the conic, we gave the directrix, we sketched it. Now we need to calculate dy dx as a function of theta. So r is equal to, I'm going to write it as 2 times 3 plus 3 sine theta to the minus 1 power to make it easy to take the derivative. R primed is equal to minus 2 times 3 plus 3 sine theta to the minus 2 power times 3 cosine of theta. Now that I differentiated it, I'm going to make it into a rational expression again. So I have 2 times 3 is minus 6 cosine theta, living on top of 3 plus 3 sine theta squared. So I have r, which I will copy from up here. I have r primed, and I know that x is equal to r cosine theta, and y is equal to r sine theta. Dy dx is equal to r primed times r prime times sine. I'm going to just go ahead and put it up on top there, plus r, which is 2 over 3 plus 3 sine theta, times the derivative of sine, which is cosine. And that's just the numerator. Now we have the denominator. The denominator would be minus 6 cosine theta over 3 plus 3 sine theta squared times cosine of theta, because we're looking at the derivative of r times cosine. Derivative of cosine is minus sine. R is 3 plus 3 sine theta. I put the negative out front, and I have 2 sine 3 plus 3 sine theta. Okay. Leave it. If you're asked this on a test question, you don't need to simplify any of that stuff. You can just leave it. Now, determine values of theta where tangent lines are horizontal and vertical. Yeah, you're going to need to do some simplifying. So I'm going to copy stuff to the other side of this page. I just copied dy d theta to the back of my page. And I'm going to set this equal to 0 to figure out what horizontal tangents are? Well, I need a common denominator. So I have minus 6 cosine theta sine theta plus 2 cosine theta times 3 plus 3 sine theta. And then all of that would be over 3 plus 3 sine theta squared, because I had to multiply this one by 3 plus 3 sine theta. Now I'm setting this equal to 0. This is equal to 0 when the numerator is equal to 0. The denominator is equal to 0 when theta is 3 pi halves, but this function is not defined there because that's a 0 in the denominator of your original function. So we don't have to worry about that. We can just look at the numerator. So I have minus 6 cosine theta sine theta plus 2 times 3 times cosine theta, and then 2 times 3 is 6 cosine theta sine theta. Oh, look. That goes away. All I really have is cosine theta, which implies theta is equal to pi halves, or 3 pi halves, but 3 pi halves doesn't exist, so, and now let's look back at my picture. Oh, look at that. Yeah, it does have a horizontal tangent at 3 pi halves, at pi halves, excuse me. So now I'm going to write down dx d theta. Once again, I need a common denominator. I have 3 plus 3 sine theta squared and just 3 plus 3 sine theta. So that means my numerator has minus 6, and I had cosine times cosine, so I just wrote it cosine squared. Then I have minus 2 sine theta times 3 plus 3 sine theta. And all of that will be over 3 plus 3 sine theta squared. Same reasoning. The denominator is equal to 0 when theta is 3 pi halves, which is not in the domain of this function. So I really just need to figure out when the numerator is equal to 0, and that would be when 0 is equal to negative 6 cosine squared theta minus 2 sine theta, oh, not 2, 2 times 3, which would be negative 6 sine theta, and then minus minus gives me, minus plus gives me minus 6 sine squared theta. So now I have minus 6 times cosine squared theta minus 6 sine squared theta. Let's just divide everybody by minus 6 because everybody has the same coefficient. So 0 is equal to cosine squared of theta plus sine of theta plus sine squared of theta. Cosine squared plus sine squared is equal to 1. So sine of theta equals negative 1. Theta is 3 pi halves. Nope. That one's not in the domain. There are no places where this parabola has a vertical tangent line. So we have one place with a horizontal tangent, no places with a vertical tangent. Now loop back up and do number 1. We already took a quick look at it and figured out the eccentricity is 4 over 5, so you know it's an ellipse. So work on it on your own. We'll come back and compare answers. Okay, this problem proves that not all of the problems come out with pretty numbers that live on the unit circle. So first we'll just graph it, which isn't too hard. We already knew it was an ellipse. We had figured out the eccentricity was 4/5. It has sine, so your directrix is y equals -1, because E times D has to be equal to 4/5, and since E is 4/5, then D has to be equal to 1. I plugged in my points. I got 4/5, 4, 4/5, and 4/9. Here's the line y equals -1. If you really needed to know what that other focus was, then you would look at the distance from this vertex to the focus is 4/9, so it would be here 4/9 units in the other direction, and then your other directrix would be up here, the same number of units away. So this was 4/9, 6/9, 6/9. So 4/9 and 5/9, not 6/9. Okay, there we go. So we've got our little graph. We did our derivative. So first I wrote it with a negative exponent to make it easy to take the derivative of. Then I wrote it back as a fraction again. And then I did not write down that x equals r cosine theta, y equals r sine theta to remind myself. For dx d theta on top, I have r primed times sine plus r times the derivative of sine, and then I had r primed times cosine minus r times sine, because negative sine is the derivative of cosine. Then I copied them to the other side of the page. I got tired of writing, so I acknowledged the fact that this is going to be equal to 0 when its numerator is equal to 0, but I did have to get a common denominator to figure out what my numerator would be. Then I went ahead and solved it, and I got theta as pi halves, or 3 pi halves, which is exactly what I expected because I have horizontal tangent lines at the tippy top and at the bottom. Then I just checked that denominator to be sure that there are no zeros there to cause trouble, and there aren't, because 5 minus 4 sine theta is equal to 0 when sine of theta is equal to 5/4, and that has no solution. Then I looked at the numerator, and this is the one that didn't come out with a pretty number. I ended up with the inverse sine of 4/5, and then pi minus the inverse sine of 4/5. And yes, I do have to draw myself a little cheat sheet to remember what the other one is. You know, your calculator gives you one that lives over on the right-hand side of the unit circle, and then you have to figure out the other one. So it was pi minus sine of 4/5, arc sine of 4/5. And because I like to make sure I'm right, I put those things into Desmos. So first I just graphed the function. Then I made myself a little function f of x so that I wouldn't have to plug that in over and over again. I made myself a variable named a that was the arc sine of 4/5. Then I plotted the point, or the line, x equals f of a times cosine of a, because that's the x coordinate on the ellipse when your input is arc sine of 4/5, and I can see, yes, that is where the vertical tangent is. And then I did another one for pi minus inverse sine of 4/5, and It's the one on the other side. So those don't always come out with nice, pretty unit circle numbers. Okay, now you know that the next one is going to be a hyperbola. Give it a try on your own, and then we'll compare answers. I had to work to draw a picture of this one that I thought was good enough. Okay, so I did the plugging in. I figured out it was a hyperbola because I divided everything by 4 and the eccentricity was 2. I found that my d was equal to 3 over 8, so the directrix was at x equals negative 3 over 8 because cosine and minus sine. I plugged my numbers in and I got negative 3/4, so I knew that was the outsider, the one that gets the reflection. And then these 3 were positive, 3/4, 3 over 12, or 1/4, and 3/4. So these are all here, 1, 2, 3, right there along the y-axis. So 3/4, 1/4, negative, or 3/4 and pi, 3 pi halves. So at pi halves, we go up 3/4. At pi, we move 1/4. At 3 pi halves, we move in the positive direction, 3/4. So we end up with these. And then I had to draw the point where I knew 3/4 was, and then I measured that this was 1 unit away. I measured 1 unit and drew, or 1/4, which was 1 unit on my scale, because I scaled it to 1/4. I plotted those points and played connect the dots. So, yeah, that one took a little bit of work. I couldn't just eyeball it. Then I went through all of the calculus to find the derivative. Set the numerator equal to 0. And I ended up with cosine of theta equals 2, which has no solution, which makes sense because there are no horizontal tangents. If the derivative, either dy d theta or dx d theta, is undefined, if there's a 0 in the denominator, then the original function is undefined, so we don't have to worry about those. So then I looked at dx d theta, and that's equal to 0 when negative 12 times the sine of theta is equal to 0. So when sine of theta is 0, or at 0, vertical tangent line, and at pi, vertical tangent line. So a lot of this is just kind of applications of the section 10.4, where we learned about conic or polar coordinates in calculus, and now we're just applying it to conic sections in polar coordinates. So your game plan: you're given a polar version of a conic, you get it into the proper form. So divide to get proper form. You determine your eccentricity. It's the number sitting right next to the trig function. Use E to determine the type of conic. E is greater than 1. Hyperbola. E equals 1. Parabola. E less than 1. Ellipse. Determine D, because ED is equal to the numerator when you're in that proper form. And let's write the proper form, ED over 1 plus or minus E cosine theta, or ED over 1 plus or minus E sine theta. And directrix, x equals, if you have cosine in your function, y equals if you have sine in your function. Plus, if you have plus sign in your function, and minus if you have a minus sign in your function. So sine is same as in your function. Then, to sketch your graph, plot the big four. Parabolas always have one undefined. Ellipses are easy. Hyperbolas always have a negative guy, an outcast. That's where the reflection lives. And then derivative, setting numerator and denominator equal to 0, all of that is exactly the same as it was for just regular polar calculus. So you have learned everything that you need to know. Now go forth and study, and you can do it because you are smart.